Hello all, welcome to the week 3 of the course Introduction to Machine Learning. In the previous classes, we have learned about linear regression. Today we are going to discuss about logistic regression. So let's recap about linear regression. So in linear regression, we have a set of examples denoted by x, which is of size n to p plus 1. We can write it as these are the number of features. We have xp, so p features, and uh, a dependent variable y which we want to predict. So this is a continuous variable. So so if we have data like this, so this is the linear regression line that we used to fit in the linear regression problem. And so the predicted value y cap is written as x into beta, where beta are the coefficients, is the matrix of coefficients that we are trying to estimate. And for that we have objective function which is a sum of squared error, which is actually the from vertical distances from this fitted line, and we can write it as sum squared error as y minus y cap. So this is the predicted value for ith example, sum over all the training examples. It can be written as y minus x beta transpose in the matrix form, and taking a derivative with respect to beta, we will get minus 2x to the power x transpose and y minus x beta. So since this is a convex function, a quadratic function, it will follow a convex shape to get the minima of to get the betas where this minima occurs for this function. We need to equate this to 0, which will give a estimate for beta. as x transpose x inverse x transpose y. And using this estimate of beta, we can predict the value of y beta x. So this will be the predicted value for the obtained betas. Now let's extend this idea for classification problem. So we have x beta, and this is the estimate we have in linear regression. So rather than this, we model this as a log of odds, which is actually probability of some class, suppose A, divided by probability of other class. So here we are talking about binary classification, problem, and this is a linear combination in betas. This function is called logit function, and this ratio is called odd ratio. From this we, so let's write, uh, so how we can interpret it. So suppose we have two classes like this and like this. So suppose we have a point P, a new point P, and we found out the probability of having of event A at point P. PA is something like 0.8, and probability of other event, which is, suppose this is event A and this is event B, probability of event B, which is 1 minus probability of event A, is 0.2. So the odd ratio will be PA is 0.8 and 0.2. So if this ratio is greater than some threshold, then we can say this point belongs to class A, and if it is less than the threshold, we can say it as the class it belongs is class B. So using the same idea, uh, we we extend this idea to this equation, and writing PA as probability of given data for class A as probability of x, we can write the same equation as log of probability of x divided by 1 minus probability of x equal to x beta. You can write this as probability of x equal to 1 by 1 plus e to the power minus x beta. So this is called logistic function, logistic or sigmoid function, and this has a shape as like this. Suppose on this axis we are showing x beta, and on this axis we are showing the probabilities. Then this curve lies between 0 and 1, and we can select some value of some cutoff value, where we can say that above to this will be class A and below to this will be class B. We can have some threshold set on this curve. So let's go back to the equation, and how can we maximize the probabilities? All so in case of linear regression, we try to minimize the sum of squared error, but here, since it is related to the probabilities, we try to maximize the likelihoods, and we can write the likelihood function of betas as beta naught betas equal to product of probabilities of all the training examples, where we take both the probabilities, the probability of event A and probability of event B, which we can write it as probability of x for training example I to the power the class of the actual class of training example I, which can be y I, and the probability of other class, which is 1 minus y I. So, and taking the log of this likelihood, we can get log likelihood as L small l beta naught betas equal to sum of y I p x i's plus sum of 1 minus p, sorry, 1 minus y I and multiplied by 1 minus p of x I. So taking the differentiation with respect to betas, we will get delta L by delta beta we will get delta L by delta beta as sum over I equal to 1 to n and yi minus p of x of I multiplied by xj for the ith training example. So this is for beta j. So this is in the exponential form. So to solve this, we can use Newton-Raphson method, and in the Newton-Raphson method, the this is an iterative method where we get betas by starting with some guess, and we update the betas using the below formula. So beta new equal to beta old minus delta L del L by del beta and del L square del beta square. So for if we apply this, we will get this as beta old minus x transpose w x inverse, then x transpose y minus px. So this can again be written as x transpose w x inverse, then x transpose w and x beta old plus w inverse yi minus I. So this is the way we can find the optimal betas. And this is uh, we will continue with a linear discriminant analysis model in the next lecture. Thank you.